Welcome back to The Explainer. Today we're tackling something absolutely foundational, a paper from Gerald M. Welch's Unified Spacetime series that literally asks us to rethink how we measure the cosmos. It's the second paper in the Unified Dimension series, and it's all about the philosophy of cosmic measurement. Now, quick caveat before we jump in, we are not here to review general relativity, and we definitely aren't trying to rewrite Einstein's math. Instead, we're going to dive deep into the underlying concepts, the actual ontology of how we measure our universe. So let's jump right into the big question. Einstein brilliantly proved that time and space are relative to the observer. You know the drill. Different gravitational environments mean different measurements of time and space. But here's the catch. If every physical measurement is fundamentally local, how do we make those measurements meaningfully comparable across the universe? How do we know what a local measurement actually means in the grand scheme of things? Put simply, when we measure something in space, we have to ask, compared to what? Here's how we're going to break this down today. We'll start with the problem of local measurement, then look at why science absolutely requires calibration. From there, we'll uncover relativity's hidden implicit assumption, explain the Minkowski Horizon, distinguish between geometry and universal calibration, and finally, see how this all fits into the broader unified dimensions progression. Let's get into it. Starting off with Section 1, the problem of local measurement and the real challenge of internal correctness. Okay, think about atomic clocks. General relativity beautifully showed us that an atomic clock sitting right here on Earth and an orbiting atomic clock up in space are going to tick at slightly different rates. And if you bring them back together, they're going to disagree on how much time has actually passed. But here is the wild part. Neither clock is broken. Neither observer made a mistake. Both are perfectly internally correct. They just disagree because they exist in entirely different realized space-time conditions. This perfectly illustrates our point. Just because you're locally correct doesn't mean your measurement is universally comparable. Being right in your own local bubble doesn't magically translate to someone else's reality unless you have a standard bridge to connect the two. Which leads us perfectly into Section 2, why science requires calibration, the true baseline of metrology. Just think about the tools we use every single day, whether you're grabbing a ruler to measure length, checking a thermometer for the temperature, or just looking at a clock. That measurement only means something because it's been calibrated against a reproducible reference condition. A lab scale doesn't give you an accurate mass because that specific lab happens to have superior gravity. It works because its measurement is tied back to a universally accepted, calibrated standard. This idea of calibration isn't just a nice to have. It's the absolute bedrock of all mature scientific disciplines. I love how Gerald M. Welch puts it. He says, without standards, measurement degenerates into isolated observation. Calibration transforms observation into science. That right there is our core thesis for today. Unified spacetime suggests we have to take this exact same foundational principle of calibration and apply it to the fabric of realized spacetime itself. Think about it. If our measurements of time, space, and inertia are constantly changing based on local curvature, then meaningfully comparing them absolutely demands a universal normalization condition. We need a standard. Moving to Section 3, relativity's hidden implicit assumption, the zero mark. So whenever we say a clock near a black hole is running slow, we really need to pause and ask, slow compared to what? Right now, standard physics leans on an implicit assumption called asymptotic flatness. Basically, it treats a hypothetical, infinitely distant, perfectly flat spacetime as the zero mark. When we define things like the mass of isolated systems or escape velocities, we're basically imagining a spot infinitely far away from all gravity, assuming the spacetime out there is perfectly flat and needs zero correction. But, and this is a massive but, here's where we have to ask that recurring question. Compared to what? If our universe is actually expanding, and on the largest scales it's dominated by repulsive energy, well then an infinitely flat spacetime doesn't actually exist. An observer traveling infinitely far away from all the galaxies wouldn't arrive in perfectly flat space. They'd end up in a highly repulsive environment. So if the zero mark on our cosmic ruler points to a place that literally cannot physically exist, what exactly are we comparing all these measurements to? And that brings us to Section 4, the Minkowski Horizon explained, a realized standard. This is exactly where unified spacetime steps in and proposes the Minkowski Horizon as our universal calibration condition. Instead of pointing to some impossible hypothetical infinity, this is a physically realized state, and it's defined by two very specific things. First, curvature balance. That's the precise boundary where local attractive gravity perfectly cancels out the universal repulsive background, creating true local flatness. And second, it has to be at co-moving rest, meaning it's completely at rest with respect to the local cosmic expansion, totally removing any ambiguity about velocity. Now, it is absolutely crucial to be clear about what we are rolling out here. The Minkowski Horizon is not the center of the universe. It is not some preferred reference frame that suddenly invalidates relativity. It's not a new particle, and it's not a new force. It's simply a metrological baseline. Think of it like sea level right here on Earth. Sea level is our universal zero for measuring altitude, right? No one goes around saying the ocean is a preferred observer. It's just the baseline condition that allows our local altitude measurements to be universally comparable. Sticking with that sea level analogy for a second, human surveyors obviously can't always access the ideal mathematical sea level every time they make a measurement, right? Instead, they use physical tide gauges as a localized working standard. Well, unified spacetime uses that exact same two-tier approach. The Minkowski Horizon is the primary ideal standard, but for actually making real-world measurements, the theory introduces what's called the Tucker horizon. This is the working standard, a finite, physically locatable boundary surrounding any mass concentration where that local gravity and universal repulsion perfectly balance out.
Let's look at Section 5, Geometry versus Universal Calibration, a crucial distinction.
We really need to draw a hard line here between Minkowski spacetime and the Minkowski horizon, because they are not the same thing. Minkowski spacetime is the established mathematical geometry of special relativity. It's the math that describes flat space. The Minkowski horizon, on the other hand, is the physical calibration condition that tells us where that flatness actually physically occurs in a universe that is dominated by repulsion. They don't compete, they're totally complementary. One gives us the geometry, and the other provides the universal calibration. We're literally just giving the math a physical place to stand. Finally, Section 6, the Unified Dimensions Progression, Building the Framework. Remember, this paper is intentionally focused on ontology, laying down the hardcore conceptual foundations before we ever touch the complex math. So let's see how this all builds. Paper 1 tackled the foundational question: what is a realized dimension? Now, Paper 2, which we've just unpacked, introduces the Minkowski horizon to answer, compared to what? And that sets up a perfect launchpad for Paper 3, which introduces the KGN framework to mathematically ask, in what realized state? Finally, Paper 4 will ask, what behavior actually emerges from that state?
So, here is the huge takeaway for today. Calibration has to precede mathematics. You simply cannot map the universe if you don't actually know where the zero mark on your ruler is. So I want to leave you with this provocative thought. Once we stop measuring our universe against an impossible, infinite void, and finally normalize our measurements to the actual, physically realized fabric of a repulsive cosmos, what hidden realities and what entirely new behaviors of the universe are just waiting for us to uncover? Thanks so much for exploring this with us.